Thank you. Hello, everyone. As you said, I'm Anjo, and this is joint work with my colleagues from the Max Planck Institute for Software Systems. And in this work, we demonstrated how to securely and efficiently isolate sensitive data within the same process using memory protection keys. Memory protection keys is a recent hardware feature in x86 as well as Power architecture that allows an application to selectively control access to a subset of pages. But before I talk about isolation, let's first look at the drawbacks of an application without any in-process isolation. So when sensitive data is not isolated, it is vulnerable to being leaked and corrupted by bugs and malicious attacks. For instance, a malicious attack could exploit a security vulnerability and simply leak the key or your sensitive data. In the past, we have seen widespread attacks against sensitive data, like the Heartbleed bug, which basically leaked private web server keys all over the internet. More generally, though, we see that memory safety issues account for a large number of reported software bugs, and this was recently reported by Microsoft. Well, we all also know that protecting sensitive data using isolation is a very good idea. In that case, bugs and security vulnerabilities are unable to leak and corrupt data. For instance, we can isolate the cryptographic keys from the untrusted application and permit access only via a very narrow interface, for example, the decrypt and encrypt functions. An attacker inside the untrusted application can no longer directly access the key and leak it. A memory-safe language and its runtime provide memory safety. But when they start using a native library written in an unsafe language, the runtime becomes vulnerable again. To avoid a bug in the native library from violating the managed runtime security guarantees, it has to isolate itself from the native library. Unfortunately, today's applications make only limited use of the isolation techniques that we have due to the lack of efficient and robust memory isolation techniques. I'll quickly clarify the threat model that we considered. So we consider the CPU, the OS, and our isolation technique to be trusted. We don't trust the application, but a small trusted compartment. In particular, we allow malicious attacks to exploit memory corruption and control flow hijack attacks. On the other hand, we do not consider side channel, row hammer, and microarchitectural attacks. Based on this threat model, I'll quickly go over the drawbacks of existing isolation techniques. In case your isolation technique relies on hardware-provided isolation, such as a page table, you typically find high switch costs between the untrusted application and the sensitive data. In contrast to these techniques are language and runtime-based techniques, which incur no switch cost, and they isolate by instrumenting the untrusted application with bounce checks on every indirect memory access. Such techniques have to be combined with a control flow integrity technique to prevent a malicious attack from circumventing the instrumentation that we just added. As a result, they suffer from high execution overheads to perform these safety checks. Our goal with ERIM is to avoid both the costly context switches and the high overhead for the execution and performing the safety checks. We achieve this by relying on memory protection keys and strengthening its threat model. So before I provide you the overview of how ERIM works, I'll quickly introduce memory protection keys. As said, it's a new ISO extension for x86 and Power and has become available in Skylake server CPUs. It allows to tag a memory page in the page table entry with a protection key. All pages start with a protection key 0. And using a new system call, an application can update the protection key of a page and assign it to one of 16 protection keys. Access to memory pages of a particular protection key is controlled via a new processor register called PKRU. And this permission register holds a read and write bit for every protection key. At application start, only protection key 0 is accessible. To enable or disable access to data in a particular protection key, a new user space instruction called WRPKRU updates this permission register. This user space instruction is what makes ERIM very fast. In our experiments, we observed a single switch to take between 11 and 260 cycles, depending on the pipeline state of the CPU. The fastest page table switch based on VM-Func takes at least 330 cycles in our experiments. And after we updated the permission register, data of a page simply becomes available. So using memory protection keys, an application can divide its address space in up to 16 memory domains. and selectively grant access with relatively little overhead. Unfortunately, this fast user space switching makes memory protection keys vulnerable to malicious attacks. A malicious attack can simply create its own permission register and create its own permission register update instruction to grant access to all protection keys. Hence, by itself, memory protection keys cannot prevent malicious attacks. So here is the overview of ERIM and how we prevent this privilege escalation. We isolate the sensitive data in a trusted compartment in pages marked with protection key 1. And then we prevent malicious attacks from gaining access to this protection key 1 in a two-step approach. We first define a safe way to switch between the untrusted application and the trusted compartments using call gates. And second, we prevent an attacker from executing instructions that would violate our isolation guarantees for the trusted compartment. ERIM prevents this by vetting all executable memory before enabling the execute permission. In case ERIM finds a violating instruction, it would simply halt the execution. At this point, the attacker is unable to circumvent ERIM's isolation guarantees. In the process, though, ERIM may stop the execution of some applications. These applications are not in line with ERIM safety checks, and this is the result of including inadvertent instructions that update this permission register. To enable the execution of such applications again, we have devised rewrite strategies to eliminate this permission register update instructions while maintaining the semantics of the binary code. Our rewriting approach has already enjoyed a lot of independent interest and has already been adopted in several work. Lastly, we take this isolation technique and apply it to frequently switching use cases and observe a substantially lower overhead compared to prior art. So before I tell you how we prevent the malicious attacks, I'll quickly introduce the two culprit instructions. The first one is write PKRU. It simply takes the EAX register and writes it into the PKRU register. The second one is XRSTOR, which loads the register from a given memory address. Our goal is to prevent an attacker from making an unsafe use of each of these instructions. So at first, we define a safe way to use them using call gates. And we switch between the trusted and untrusted compartment using these call gates. This technique is what makes ERIM very efficient. When we switch from the untrusted application to the trusted compartment, we increase the permission register to grant access to the trusted compartment and immediately call a designated entry point in the trusted compartment using a direct jump. Afterwards, the trusted compartment will guarantee to reduce the permission register before handing back the execution to the untrusted application. When we are switching back to the untrusted application, the permission register has to be updated to exclude the trusted compartment. But without any further protection, that particular write PKRU is vulnerable to an attack where the malicious attacker updates the EAX register to include the trusted compartment in the permission bits. And then a new control flow hijack directly jumps to the write PKRU to update the register. Afterwards, the control would again continue inside the untrusted application, violating our trusted compartment security guarantees. So this attack requires us to add another safety check after the write PKRU instruction. With this check, we ensure that the access permission has either been reduced to the untrusted application only or the execution stops. So now we can use safely write PKRUs. Our goal has become to eliminate all unsafe uses of write PKRUs in XRSTOR. ERIM prevents the execution of pages that include such unsafe write PKRUs in XRSTORs by vetting every memory page before enabling the execute permission. Therefore, we monitor the untrusted application and remove the execute permission from system calls that set the page permissions. As a result, the execution of a new page without any execute permission leads to a page fault. ERIM's trusted page fault handler at this point is invoked, which again vets the page and only allows the execution to continue if it did not find any unsafe write PKRUs or XRSTORs. So given these two techniques, we have prevented an attacker from accessing the trusted compartment. In the process, though, we have introduced checks which may result in halting the execution of some applications. Our goal is now to rewrite these applications so that they do not contain unsafe instructions. This is a challenge due to the complexity of x86 and its ability to execute any byte-aligned address. The two examples I'm showing here are WRPKRU instructions sequences in the form of 0f, 01ef, which can either occur across two instructions or in one longer instruction. While these two examples focus on WRPKRU, the same holds for the XRSTOR sequence as well. With ERIM, we rely on binary rewriting to eliminate these inadvertent but unsafe WRPKRUs. So the rewriting here can be integrated either into your compilation process prior to enabling the execute permission at runtime, or statically by rewriting the binary before the application starts. We have devised 7 rewrite rules to generate semantically equivalent instructions without the unsafe sequences that you see here. In the instance I'm showing here, the WRPKRU occurs across two instructions. A simple rewrite rule inserts a no-op instruction in between the two original instructions, which would break the sequence. Rewriting the sequence within a larger instruction is more difficult. Luckily, the x86 instruction set follows a general format, and we use this format to devise rewrite rules that are independent of the instruction opcode. As a result, the rewrite rules only depend on which part the sequence occurs in. The example here is an add instruction that includes the WRPKRU instruction in the mod RM and the displacement value. We chose to rewrite the used register assignment, and therefore we first free up a register, here EAX, and alter the register assignment in the add instruction. As a result, the leading 0f changes into a 07, which again breaks the sequence. While these were just two examples, we have devised similar rules for the complete x86 instruction set, and I urge you to read the paper for all the glory details. Now we have a secure and usable isolation technique, and we would like to apply it to a frequently switching use case. Let me first tell you about our prototype. It's a user space library, which provides you the safe call gates that I talked about in the beginning, a memory allocator for the trusted compartment, and an inspection mechanism to find unsafe WRPKRUs and XRSTORs. We additionally provide you with a user space monitor and a Linux security module to intercept system calls that enable execute permissions for pages. In addition, we implemented the binary rewriting in a static binary rewriting tool, which is based on Nginx. We evaluated ERIM by asking two main questions. The first one is, how frequent do inadvertent WRPKRUs and XRSTORs occur in today's binaries? To that end, we inspected 200,000 binaries of 5 Linux distributions. We found about 1,200 WRPKRUs and XRSTOR instances in the binary code. We then used Nginx to disassemble about 1,000 of them, which is a prerequisite to actually rewrite them afterwards. And then using our rewrite rules, we were successfully able to rewrite all of the instances we were able to disassemble. In the paper, additionally, we describe a dynamic rewriting approach for pages that could not statically be rewritten. The second question we asked was about ERIM's overhead in frequently switching use case. And due to my limitation in time, I will only talk about how we isolate session keys within Nginx, a high-performance commercial web server. Today's implementation of Nginx uses OpenSSL and does not protect the keys at all. It's vulnerable to bugs and security vulnerabilities that could leak or corrupt the keys. For example, the Heartbleed bug was just a simple example. With ERIM, we isolate the AES session key into a trusted compartment and only allow access via a narrow interface, in particular the key initialization and the encryption and decryption functions. This experiment here runs a single worker Nginx instance and queries different file sizes. We compare the native throughput without any isolation to the previously described isolation using ERIM. Overall, ERIM's throughput is within 5% of the native performance, while protecting the session keys against bugs and security vulnerabilities in the Nginx server, as well as large parts of the OpenSSL. We achieved this high throughput despite performing 1.3 million switches per second in this particular experiment. Existing techniques can simply not sustain such high switch rates. In case of VMFunk, it has a 3 times higher switch cost. Similarly, runtime-based techniques, even if they use hardware-provided bounce checks, cannot perform at the rate of ERIM. At larger file size, this particular experiment becomes network-bound, at which all techniques actually achieve a similar performance. So to summarize, ERIM efficiently and securely isolates sensitive data within the same process using memory protection keys. We protect against malicious attacks by creating safe call gates and monitoring the executable memory. We overcome the limitations of ERIM's environment by devising rewrite rules that create runnable binaries again. Our extensive evaluation has shown that ERIM can be applied to frequently switching use cases, and we observe a substantially lower overhead compared to prior art. With that, I would like to thank you and mention that our code is available, so feel free to check it out, and I'd be happy to take your questions. Thank you.
Jeffrey Yao from UC Irvine. Yeah, fantastic work.
Thank you.
Lightweight contacts use two set of page tables to protect in-process memory. So actually last year in CCS, there's a work called Mikomi that also used two set of page tables, and they also use call gates very similar to this design. Mm-hmm. Do you think that is enough, or what's the benefits on top of that?
So call gates itself have been, I think, invented quite a while back, right? So for sure, we have a newer call gate that's like, it has to be adopted into the technique that you're using, true. But I think the benefit here is that we show how we actually enable a stronger threat model by allowing the rewrites, right, once we eliminated the unsafe sequences.
I see, thanks.
Welcome. Hello, John.
Hi, John Criswell, University of Rochester. So I had a question about the binary writing approach. So as I understand it, disassembling x86 code is an undecidable problem. So is there something about the WRPKRU instruction and its encoding where the situations where it can occur is something where you can always reliably rewrite? Or is it just the case that as it happens, you can always rewrite it successfully in your test cases? So it's something that in theory could be a problem, but in practice is not.
No, so we went basically through the entire x86 instruction set and looked at what cases exist, right? And then we devised these rewrite rules.
Right, but the question that I have is that disassembling x86 is in general undecidable, right?
Yeah, sure.
Right, so is that like a theoretical problem with your approach, or is there something about the way that the instructions are encoded that no matter how you rewrite it, it's always going to end up something that's with something that's functionally equivalent?
So the disassembly is an issue that Dynenst brings in, right? We are using actually a rewrite tool, Dynenst, which we ourselves have not written, right? The technique for actually rewriting and how they disassemble is provided by the tool itself. And they require us to disassemble x86 binaries. If you, for example, imagine that this technique would be integrated into a compiler, right? I'm
not asking about compilers because that's obviously fixable. I'm just asking about like if I give you
let's go ahead and take this offline.
Yeah, sure.
Okay.
Thanks.
All right, we have time for one more question.
I'll make it quick. Hi, Matthias Neukschwantner from Oracle. So I was wondering, you have a pretty strong threat model already, basically giving the attacker control over native code. The only thing that you explicitly exclude is essentially microarchitectural attacks. I was wondering if you thought about extending towards that direction as well, because it seems that if you would add that and you have in-process isolation that also includes that, we could get rid of site isolation.
So, it's definitely an interest. There is an interest to go into that direction, right? But we are relying on the underlying fundamentals of memory protection keys, which is implemented in hardware, right? So although we can use some of the techniques like L-fences to protect against some vulnerabilities, right? You may not always be able to protect against all microarchitectural attacks that you don't even know about.
Okay, thank you.
Let's go ahead and thank our speaker once again.